So our next speaker is, and forgive me if I get the pronunciation wrong, Luis Miguel Mea Suarez. Luis is a scholar lover working at Zebia Functional, currently working to become a professor, and he is going to be describing some lessons learned from implementing an efficient functional mutex. So, welcome, Luis.
Welcome and thank you for having me. Yeah, the pronunciation was Kozakli. I think Spanish names are kind of normal to pronounce, but I'm biased. That's my mother language anyway. Um,
Well, I will hand the stage over to you. Go for
Thank
it.
you. Okay. So yes, they mentioned I will be talking about the story of how the current implementation of mutets in CatSFA came to be. Let me share the presentation and Uh, yeah, since it's looking constantly, please just stop me if it doesn't move constantly. So a little bit of context before I started with the how the current version of mutex came to be in CatSFX. So first of all, what is a mutex? So a mutex is a concurrent data structure that provides a group of fibers with mutually exclusive access to a shared source of critical section, and it is semantically equivalent to a semaphore. So let's digest that a little bit. First of all, mutex is a concurrent data structure, and the keyword here is concurrent, like the whole point of this talk is about concurrency. So what does concurrency means? It probably have a lot of better descriptions than what I'm about to say, but I usually just think about it. You have a multiple threads of execution in the CatSFX world that will be fibers that are trying to access something or trying to use something at the same time. And that usually can lead to trouble if you don't coordinate things correctly. A mutex is a way to coordinate those things, those multiple threads of execution correctly with a mutually exclusive access, meaning only one of all those fibers, of all those threads of execution, can actually use that resource or access that space of code, that lines of code that you want to run completely exclusive from everything else. And essentially, as it says, it's just like a semaphore, because a semaphore gives you exactly this, uh, but a semaphore is tended for allowing more than one fiber at the same time. So usually when you create a semaphore, you say, I want to only allow 2, 3, 5, 10 fibers at the same time. If you only allow one, you have a mutex, right? And actually, sorry, if you want to see if it's a Scala interface, it looks like this. Mutex, which just have a single method, lock, which gives you as a source of unit. For simplicity, I am hard coding IO everywhere, so this is like the source of IO. Obviously, the real CatSFX version has like an F, but yeah, just you can think of it just as the source of IO. And as I mentioned, actually the original version of Mutex, which was added back as the September of the previous year and released in version 3.3.0 of CatSFX, if my memory serves correctly, was essentially just a wrapper of a semaphore of a single permit. So we created a semaphore, and then the lock was just acquiring a permit from the semaphore. And that's it. That's all that it did. However, we wanted it to be a little bit more efficient. Like semaphore is very efficient, don't get me wrong, but semaphore is intended, as I mentioned, to have more than one permit. The one permit case is not optimized because it's not that common for a semaphore. And it means that these mutets have to deal with a lot of indirections. Like it has a wrapper over the semaphore. It has an indirection because the mutex is just calling the semaphore. And the semaphore, as I mentioned, is intended for more than one permit. So it has logic for allowing more than one fiber at the same time. It has logic for managing a release and awaking more than one single fiber and all that. Whereas for mutex, we only want one in and one out. It should be a lot more simple, so it should be more efficient. So Arman and I started thinking about it, and it all started as a couple of conversations on Discord. After a couple of days of me thinking how to make it more efficient, I have this first plain and simple idea that I call LOT Q. So what is a load queue? Well, I just realized that a mutex is kind of as a single person ride in an amusement park. So we have this attraction here, like this Chicago Well, I believe is the right name in English. I imagine there's can only be one person here. So being here means you have access to the mutex. It has a door. And in this case, since the first situation is that the mutex is free, the door is open. And what will happen is that when a fiber arrives and tries to use the mutex, tries to acquire it, it sees the open door, it acquires the mutex, closes the door, uses the mutex, so it's kind of like being in the amusement park. And then when it is free, when it finishes, it releases the resource, and releasing the resource is like putting the door open again for the next fiber to arrive, right? Pretty simple. And then the fiber leaves. And yeah. Now, second situation. What if the mutex is already occupied? So just like before, we have the fiber already in the mutex, we have the closed door. Then the second fiber arrives, and contrary to the first one, it sees that the door is closed, so it cannot acquire the resource immediately. Rather, it waits for that door to be free again. So this suspend the fiber. Remember that in CATS-FA, of kind of blocking, sleeping, all that semantically, there is no real physical thread being blocked, but the fiber is blocked. The fiber is waiting for the door to be open again. When the first fiber finishes and releases the door will notify the second fiber that it is free, so the second fiber can just go ahead and close the door again. Again, very simple stuff. Now let's go with a more complex situation. What happens if we have more than one waiter? So same situation as before, but now we have a third fiber arriving and try to use the mutex. We can't have this third fiber await for the same door as the second fiber is awaiting, because when the first fiber finishes and notifies the door, releases the door will notify both fibers, and then both will acquire the mutex, which will break the contract that only one fiber at the same time can be using the mutex. So in reality, what is going to be happening is this. Every time a fiber tries to acquire the mutex, if it doesn't acquire it, if it finds a door, what it's going to do is put like another door behind them. So the third fiber will actually not see the door that the first fiber left, but rather will see the door that the second fiber left. That way, when the first fiber finishes, it releases its own door, which notifies the second fiber can go. And when the second fiber finishes, it will release its own door, notifying the third fiber, and the third fiber can go, and so on. And since this is CATS-FA code, we need to think in a final fourth situation, which is cancellation, because all CATS-FA code has to be cancellation safe. You should be able to always cancel a fiber that is waiting for something. So let's have the same situation as before. We have fiber 1 using the mutex, 2 and 3 waiting in that order, and then imagine that the second fiber gets canceled. If that happens, what we are going to do is the following. We are going to step off of the queue of waiters. We are going to notify our door, so this will awake fiber 3, but we need to tell fiber 3 that the mutex is not free yet. It's just that we that were ahead of them in the queue are going, so they could await for wherever we were awaiting for. So again, imagine just this, like a couple of people waiting for an attraction in an amusement park. So what we do in this case, that when we notify our door, when we release our door, we release not with the empty door, which is what we do when we actually and using the mutex, we release it, but given another door. So that way, the fiber 3 was notified, and the fiber 3 receives the next door that it needs to await again. So it is awakened to sleep again. And that's it. That's basically it. So you might say, well, Luis, all those cases look pretty simple and straightforward. So what is the point of the talk? Did the organizers get out of ideas and have to invite you out of pity? And probably yes, but there is actually a big deal here. And what big deal is in the details. And in the details, this case, are concurrency. So once again, the point of all this talk is concurrency. All those situations that I just explained work very simple because I'm always assuming a happens before relationship. I am saying fiber 1 is here, fiber 2 is here, fiber 3 is here. I always say fiber 3 ends in the scene after fiber 2 was already there. So this is all pretty sequential. But in the real life, since we have concurrency, what is going to be happening is that all these things might be happening at the same time. This cancellation might be happening at the same time that fiber 1 is releasing the mutants. This cancellation might be happening at the same time that fiber 3 is reaching. It might not already be here. When fiber 2 and fiber 3 wants to acquire the mutex, we don't know which one was fiber 2 and fiber 3. We actually just have two fibers trying to acquire the mutants at the same time, right? So the point of the implementation is to make sure that we always have this happens before relationship between two concurrent events. The mutants works perfectly. The design that I just mentioned works perfectly if we always can say the cancellation happens first and the release, or the release happens first and the cancellation, fiber 2 reaches first and fiber 3, etc., etc., etc. So this is the point. We need to make sure that we can always create this happens before so that the implementation can be pretty simple. And it turns out that Katz effect primitives, or in general, is pretty nice to write in that kind of code. It's pretty nice to give us tools to create this happens before relationship. So this is all the code. This is pseudocode. This is omitting some details. But if you look now into the current implementation of mutex, you will see that the code is pretty similar to this. So we have the mutex. The mutex will have an state, which is a reference of what we call a log Q cell. These log Q cells are like the spaces in the example that I was painting before and these doors, right? And we have two steps, acquiring and release, and thus the log is just making a resource with acquire and release. Pretty simple. Acquire is the more complicated bit because it's the one that has to make all the logic, but it's not very complicated. We first create a deferent of another log Q cell. So this is like we are creating our space, right? So this deferent is our space in the queue. And then once we have our cell, our space in the queue, we go to the state and we get and set the last space with ours. So instead of having in the state all the places in the queue and having an actual queue of spaces, what we are going to have is just always a pointer to the last person in the queue, to the last fiber in the queue. And what we do when we try to acquire the mutex is that we go to the queue and get who was the last person and put ourselves as the last one. So again, imagine this analogy of a person going to an amusement park. When you want to enter an attraction, you only go to the last spot in the queue and you put there. That's what it's called a queue, right? So that way, the ref is with this get and set ensure that happens before relationship. If two fibers want to go into the queue at the same time, they will execute this get and set at the same time, and one will succeed, the other one will fail and will retry and succeed. But that ensures that one gets the second spot and another one gets the third spot. So this again is making sure that we have this happens before relationship, right? Once we get the last cell in the queue, once we get who was the last person in the queue, we go into this loop of waiting. So what we do is that we check if the next cell in the queue is the empty cell. If it's the empty cell, it means the mutant is free. So we go ahead and use the mutant. So we just complete this acquired loop and we are acquired the mutants. If it's not the empty cell, it means it's a busy cell, you can call it. And a busy cell is basically a deferent of another cell. of another space in the queue. So we get that. So basically, this is that get is this awaits for that we were doing here. We await for that door to be released, right? And when that get completes, we loop again. So basically, in the sequential case, this is just, oh, I am the fifth one in the queue. I await for the fourth one, and then for the third one, and the second one, and that until I actually get to the first spot. And so actually, you in the sequential case, you always only going to be notified once when the previous person from you actually finish and tells you, hey, you can go. But then we have to manage cancellation. So what we are going to do in the case of cancellation is that we are going to complete our own door with the door that was ahead of us. So again, this thing that I mentioned before. If Fiber2 is canceled, so Fiber2 was awaiting for this door on its right, what it is going to do is that it's going to notify, complete the door that it created, to which is its door on the left, and it's going to pass the door in the right. So that Fiber3 will awake and will see that what is received was not the empty cell, rather it is received another dot, so it will wait for this door, right? Exactly the same that I mentioned is what this code is doing. And then finally, releasing the mutex once you are free, once you finish using the mutex and you want to release it, basically you complete your cell with the empty cell. So basically, again, going back here, all that we did in this first example. Right here, when you finish, you go and complete your door with the empty cell so that the next fiber, the fiber that was waiting for you, knows that they can just go ahead and use the mutets. So that's it. That's basically it. And again, the pretty nice thing here is that things like Deferet and Rev all guarantee that things work as we expect. The reason why this implementation is pretty simple is because CATSFX itself already tackled all the hard details, like making sure this get and set is atomically safe, making sure that this get is safe, making sure that we can cancel this get, making sure that if I complete a Deferet, I can only complete it once, and the other person will be notified, no matter if the other person is just doing the get concurrently to the complete, because remember that we are getting in one and completing in another one. So there are two fibers in place here. CATSFX takes care of all that and makes sure that everything works the way you expect it to work, right? So that was it. We could have ended the talk here and explain how CATSFX was just so great to do all this, but for some reason, Arman and I think we could do better. And don't ask me why, but we think we could do better. So the next idea that we have was blockchain. So the story began with this innocent PR that had just one commit, which was improve the mutex implementation. This was the lock queue that we just saw. And then the day before, I tried to do blockchain. And this is a screenshot of the code. And I'm not going to go there. As you can see, it's a lot of comments, a lot of bars, a lot of whiles, a lot of nulls, a lot of cast. And originally, the point of this talk was actually trying to go here and explain what this code was doing and what the mental model was. But you will see in a moment why that is not the case anymore. But you might be asking, Luis, but what was the idea? Like, what was so bad about LockQ that you wanted to do better, right? So all this mess, because this was a mess, and this is not even all the code, this is just parts of the code. All this mess was because a couple of things. First, trying to get rid of unnecessary indirections and wasted memory. This is the original version that we have here. That's what I mentioned, that currently the real code is a little bit different, but conceptually is the same. Doesn't consider the case where nobody's waiting for us. Like this code looks great if there is actually somebody already subscribed to our door, but if there is no one subscribed to our door, we are notifying no one. Um, so that was the first thing that we wanted to kind of solve, this notify to no one. Don't do that. Don't waste time doing that. Also, it has this thing, and you can see it in the animation here. So when Fiber 1 finishes, it will complete this door. When Fiber 2 finishes, it will complete this door. And then when Fiber 3 completes, it will complete this door. And if a Fiber 4 comes, what it will see is a door, because we are never actually putting back in the state the empty cell. We are putting a door. There is always a door after the first Fiber reach the mutex. So what Fiber 4 will see is a door, but it is a door that is already completed, and is already completed with the empty. So it will acquire the mutex, which is what we want, but it will go through a weird indirection of seeing a door that is actually not closed. That is because this implementation was not optimizing for the case where if you go off of the mutex and nobody is waiting for you, instead of just completing your queue with the empty cell, which is what we are doing here, we always just complete our cell with the empty cell. So we are always telling the person that is waiting for us to go ahead. We are not considering the case where there is no one waiting for us. So instead of completing our cell, we could just go to the state and put the empty cell again. That way, when the next favor arrives, it will see the empty cell and can go directly. So that was the first thing that we wanted to improve. The other thing that we wanted to improve is that when we cancel things, we were basically awakening a Fiber to block it again. So this thing that I mentioned here, when Fiber 2 is canceled, it awakes Fiber 3 and tell it, hey, you are not ready to go, rather just go ahead and wait in this new door, in this new cell. So we awake Fiber 3 just to sleep it again, which seems kind of dumb. That was our kind of rationale, that it was wasteful. So those two were kind of the main ideas that we wanted to improve. So the reason why it is called lock chain instead of lock queue is that we changed the mental model from being backwards, like where you are waiting for someone to notify you. We move things like forward, where you will tell the person ahead of you to notify you. So like imagine instead of having like a real queue, it's like you will kind of just go and hey, and tell the person that is in there and say, hey, when you are free, just call me and I will come back here and enter you. I'm behind you, just remember me. So again, the original talk was about explaining that model, when instead of leaving signals for the next fiber, we will actually leave back a box that the next fiber could fill with the signal to await them. And in cancellation, what we will do is that we will move what was in our box to the next box. And it was really a mess, but it was freaking fast. So we benchmark this lock chain, compared to the before is like the semaphore of a single permit version, and after is this lock chain version. And we have a couple of cases: happy path, where it's just one favor acute the mutets, freeze, another one's acquire first, like sequentially acquiring and releasing the mutets. High contention, which means a lot of fibers trying to acquire the mutets concurrently and then liberating them. So like a more realistic use case of a mutex. And then we have cancellation, where we put a lot of fibers to await for the mutets and we cancel a couple of them randomly. And we repeated the experiment, so the benchmark with 10 fibers, 50 fibers, 100 fibers. And as you can see, I won't go in the detail of the table, but as you can see, it was always faster than the single permit version. Even sometimes like close to 30% faster, which is a lot, but like in general, it was more or less like 20%, which is again a lot. faster. Again, this is like at a scale of milliseconds. You probably won't get your service to be blessing fast because of this change, but it was good to always try to do better. Now you might be asking, Luis, but how did it compare to the log Q? Was that mess worth it? And the answer is, we don't know. Like, one of the mistakes and one of the lessons that I want you to learn is to benchmark everything. We never ever benchmarked this version. Rather, we just went ahead to this one and say this has to be better because it's more efficient. It's not allocating, it's using bars and all that stuff that I usually criticize when some people mentioning in Discord I was a big hypocrite and doing that just like here because well, it's Cats effect, it has to be fast. So yeah, we don't know how fast this was compared to the other version. We just think it was faster. As I was mentioning originally, the tile was about that version, but then something happened. Like less than a week after we released that version, Arman came and replaced all that using something called unsafe unbound, which is an internal data structure for Cats effect. This is like the primary building block of the queue data structure in Cats effect. Is in a sense a queue for callbacks. Again, a mutex was essentially a queue of people waiting, which is callbacks. So it makes all the sense to use unsafe bound. Actually, Arman all the time was telling me, Luis, just use that. Don't waste more time. Just use that. The problem is that for doing that was like internal and private. So I have to copy paste it to a file and play with Mima. And I was just too lazy, to be honest, to do that. And I was pretty convinced that my LogChain idea was faster because LogChain was intended for a single waiter, whereas unsafe bound is intended for multiple waiters. So I still think that my idea should be better because it was optimized to that specific case, which was, again, like all the rationale from not using a semaphore of a single pyramid to be optimized for the single case. The point is that Arman made all that it was too lazy to do. And again, I'm not going to go into the details of the benchmarks. The point is that it was faster. So at this point, the point of the tile was to stand in the shoulder of giants and don't be lazy. Because unsafe bound was made by Daniel and Arman. I was like very efficient, and if I recall correctly, it's based in something called Java concurrency tools, which is also made by very smart people, way more smart than me. So I should have trusted. However, again, that's not the point of the talk. So what went wrong? Well, books and more books. It turned out that this unsafe bound version, and to be fair, actually my original LogChain version as well, had a concurrent, had a book with concurrent cancellations, right? So this is like the minimal reproduction of that book. You have one fiber which acquires the muted and haven't released it. So the muted is occupied, is busy. Then you have fiber 2, fiber 3, and fiber 4 trying to acquire the mutets. So again, all these three fibers are blocked because the mutets is already busy with fiber 1. And then we will concurrently release fiber 2 and cancel, so release fiber 1, cancel fiber 2 and fiber 3. And after all that finish, we expect fiber 4 to join. If the mutex was working currently, this should work. No matter what order these operations were actually interpreted by the mutex, it doesn't matter if the mutex interpret first the cancel of the second fiber, then the first release, then the third cancel, or in whatever order combination, because that's the point, is concurrent. We don't know what will happen. The mutex should support this. The point is that the mutex should become free for fiber 4 to use it, and basically the fiber 4 was just acquire and release it immediately. So this program should complete and should work. However, what was happening is that this program was hanging forever. For some reason, the 4 fiber was not getting notified. The mutex was left in a corrupted state where it think that it was still busy. And even worse, I actually think that if you added a 5 fiber to await after all this, the fit fiber will acquire the mutate. So it was kind of just fiber 4 were lost in the universe. So again, something that you really don't want to be in Katz effect. This is not the promise that we are making for users. Well, I'm not a contributor, but you get the idea. So Daniel Urban come and fix it, and then fix it even again, so you can get an idea how broken this was. But that fix had its own problem, which is what we call Preset-Whiteley's order in a non-size condition. Basically, what is this? We, again, have one fiber having the mutets occupied. Then we have a second fiber trying to acquire the mutets, so this one is blocked. Then we have numbers, which is a list from 1, 2, 3, 4, 5, up to 10. And what we did is that we execute all those numbers in parallel, and for each number, we will sleep that number of milliseconds, then try to acquire the mutex, and when we get the mutex, we will modify as f to put the number in the beginning of the head of that list. The f had a list of numbers. Then we will wait for a couple of milliseconds to make sure that all these were already in place. We will cancel the second fiber. We will join the first one, and we will wait for all this to finish, and then we will get the numbers. And we expect that to be 10, 9, 8, because look that each number is waiting more than the previous one. So even if all this is running concurrently, in theory, this test is actually fully sequential. You have multiple fibers, but all fibers are actually running in order. You have the first one using the mutants, you have the second one blocked, you have the number 1, number 2, number 3, number 4, etc., 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 in that order. So you expect that after all this running, you expect the ref to have the numbers in reverse order, because we are prepending rather than appending. So if we reverse that, it should be the same as the numbers, right? And what was happening with when this pair got merged, what was happening with that version is that this cancellation break the way this works. Like the fix that Daniel Urban got to managing cancellation and about the previous book was to schedule some fibers, but that break this FIFO order. So what was happening is that actually the final list was like 1, 10, 9, 8 until 2. So the first one that should have been the first one to run was actually the last one to run. So it was not only messing with the order, it was a massive change in the order where the first waiter was becoming the last one. And it's not only that FIFO is like a good warranty to give, even if Mutix technically doesn't promise it, and not even today, but it does, which is something nice for you to have, is that it was breaking fairness in a very big way, and it was also giving us this hypothetical situation where a fiber could actually never run. Because if you have a fiber and then waiting for the mutex, and then fiber that was before that fiber in the mutex waiting for the mutex, it's canceled, this fiber will go to the back of the queue. And then if the fiber that was just ahead of that one will cancel, it will be moved back to the queue and move it back to the queue and back to the queue. Again, very unrealistic scenario, to be fair, but it was technically possible. So you could create a scenario where a fiber will never run, or run after a lot of time where it should actually have run. So again, a massive change to fairness. So basically, that's what Arman said on the PR, and again was pointing out that this test was running in something that we'll call ticket in the Katz effect run suite, meaning that all this was running actually sequentially, like in order. So I was pretty sure how to fix this and this in blockchain. So I made the changes. I don't remember why CI was red in this case, but it was actually passing the specific testing local. I believe it was a Mima thing or something. I don't remember, but this, you can imagine this ZX as actually green Azures, green checks, sorry. But then, even if it passed these two tests after making the fixes, I realized in a Discord call with Arman where I was telling him all my mental model and all that, again, like the original point of the talk, we realized we have another serious bug, which was this. Cancellation must not cause up the mutex. So again, we have fiber 1 having the mutets occupied. We have fiber 2 and fiber 3 waiting for the mutets, fiber 4 also waiting for the mutex. We will cancel 2 and 3, wait for 4 to join, and then release first. This is a nonsensical program because even if 2 and 3 left, the first fiber is still using the mutex, so fiber 4.join will block forever because nobody is releasing fiber first. It's actually being released after this join happens. Again, it's a nonsensical program, so this must not terminate. CATSFX actually allows us to test this kind of programs, which is pretty nice. And the problem was it was actually terminating. Like these two cancellations were co-opting the mutets, and we will tell in fiber 4 the mutets was free, when in reality it was not free, which again is kind of the point of mutex. So this was a very major problem. And also again, this was fully ticket, like this was again fully sequential. So back to bases. Remember the lat Q that I mentioned at the beginning? Well, he's back in POC farm. Basically what we did was we reverted to lot Q. And for some reason, we tried to optimize it again because we know it's not fair to say this to Arman. I am a fucking idiot. And I tried to optimize again. And then we make some benchmarks. And this time we actually benchmarking the unself-bound version with the fixes from Daniel Urban, which have this FIFO order thing, but it was not totally convincing. We have the original log Q, finally actually benchmarked, and this new version was like log Q, but with some twins, and again trying to use not using ref and deferred, but rather using callbacks and atomic reference and bars. And as you can see, again, I'm not going to go into the numbers, even if this one was somehow better than the log Q in some cases, not in all of them, and the difference was not that big. And actually log Q again was actually even better than unsafe bound in some situations, and didn't have the FIFO order book and all that. So this story ends just where it began, which is using log Q as the final implementation of mutex. We actually later down the line added a couple of minor things, like avoiding those double indirections that I was mentioning at the beginning. We actually found a way to do this safely, and they're using some allocations to reduce memory usage. Like we actually managed to do it better, but in a more sonner way, that all that mess of code and nulls and comments and all that I mentioned at the beginning. Thus, just to finish, because I think I'm running a little bit late now, with what we learn from all the experience. First of all, thanks to Christopher, concurrency is a pain in the ass. It totally is, and that's what I love CATSFX, because it allows me not to think, well, not to think now, but have a more structured thinking about concurrency, because it gives me tools that solve a lot of these problems that give me this happens before relationship out of the box, which is very important. Then this one, courtesy of Fabio, really the mixing that is tricky. Basically, the reason why LogChain was so is because I was trying to program with imperative primitives like null, cast, atomic reference, and all that. But I was thinking they will work like programs as value primitives like ref and deferred. So again, it was this mixing of both things which was causing the issue. So something that Fabio pointed out when he was reviewing the PRs. This one, courtesy of Arman, left through different make it easy to implement surprisingly fast concurrent state machines are simple to reason about. Again, LockChain, sorry, LockQ is just a pseudo state machine. It's not totally a state machine. Semaphore is in the state machine. Look, even if LockQ was a little bit faster, it's milliseconds faster. And again, all the code is pretty simple to reason about. Then Gavin point out that composition wins as long as the primitives are fast, so complementing what Arman say. And finally, myself is going here to tell you, don't ever do this in your application code. Like never. If for some reason you will have to implement your own mutex or something similar, what you should have done is the very first thing, a semaphore of a single parameter. The use primitives that already exist. If you can't or you don't want because it's too expensive and you want to do something more performant for your specific use case, use ref plus deferent, which is LockQ, which again is pretty easy to reason about once you understand it. Don't ever go back to whiles, atomic reference, nulls, cas, and all that. Believe me, it's not worth the pain. Even as you saw in the benchmark, it wasn't even that faster than ref plus deferent. Ref plus deferent pretty optimized thanks to the Katz effect maintainers. So just use that, please. And that's it. Sorry for taking, I don't know, like 10 minutes more than expected. I hope you all enjoy it.
Thank you, Luis. That was a great illustration of how the sausage gets made internally and the difference between thinking of things for applications and how the library itself works.